In section 2.3, we're applying deductive reasoning. Remember that at the beginning of this chapter we talked about inductive reasoning, which was looking for patterns. Today we're talking about deductive reasoning, which is using facts, definitions, accepted properties, laws of logic to form a logical argument. So deductive reasoning is all about facts, okay? Cold, hard facts. You need definite reasons, you need to use definitions or accepted properties, and we're going to talk about some laws of logic today that are forms of deductive reasoning. It's all very formal reasoning, okay? It's all about facts today. Now, law of detachment, it follows from an if-then statement, and how it works is if you have an if-then statement and it's a true if-then statement, I'm going to underline that because you know that you need to have a true conditional statement, a true if-then. Remember, it's an if-then statement or a conditional statement. And you know that the hypothesis is true. If you have a true if-then statement and you know the hypothesis is true, remember that the hypothesis is the portion of the if-then statement right after if. So in this case, my hypothesis is you have a true if-then statement and you know the hypothesis is true, then you must know the conclusion is true as well. Remember that this has to start by knowing that the if-then statement you have is actually a true statement. And if you know the hypothesis or the first part is true, then you also know that the conclusion of the statement is true. I should have written also true. Okay, so an example of this, let's say we have a true if-then statement. If you remember back when we, actually yesterday when we talked if-then statements, remember the statement, if it is raining, then there are clouds in the sky? And that's a true statement. If it is raining, then there have to be clouds in the sky. Well, let's say I know that the hypothesis is true. Now in the statement, if it is raining, then there are clouds in the sky, it is raining is the hypothesis, right? Because if it is raining. So we're assuming we know the hypothesis is true. I know it is raining outside. What is a statement that you can then tell me? Well, you can tell me your conclusion is that the conclusion of that statement is also true. In if it is raining, then there are clouds in the sky, the conclusion was there are clouds in the sky. So it's starting with the true statement. If it is raining, then there are clouds in the sky. That is true. I know the hypothesis is true. I know it is raining. You would tell me, well, the conclusion is true. So you would tell me there are clouds in the sky. Okay, that's how law of detachment works. Law of syllogism is also sometimes called the chain rule because it involves more than one statement. Let's say you have one if-then statement, and I'm just doing variables here for the hypothesis and conclusion. So if P, then Q. If, I don't know, if it is raining, then there are clouds in the sky. And then you're going to have another statement, except for whatever the conclusion was of the first one, which I had called Q there, is going to be repeated as the hypothesis of the next one, of the next if-then statement, and then there's a conclusion to that one. So we really need to notice the fact that this statement was the conclusion of the first statement and then the hypothesis of the new or the second statement. Now if I know that both of these statements are true, and I have to know that they're both true for this to work, it's basically making a chain, like we call it chain rule, law of syllogism. I'm going to ignore this common conclusion and then hypothesis here and sort of start at the beginning and say, well, if these are both true, then I know that if I start with if whatever the very first hypothesis was here, I know that these are going to connect. This will be true, this will be repeated and true again, and I can go right to the end and say that the conclusion R would follow from this very beginning point, from this hypothesis, because this portion was repeated. Now with that statement, if it is raining, then there are clouds in the sky, let's say there's another statement, but I have to repeat the conclusion as a new hypothesis. So if it is raining, then there are clouds in the sky. Repeat that. If there are clouds in the sky, then it is not a completely blue sky. Okay, that could be our second one. So if it is raining, then there are clouds in the sky. Repeat that. If there are clouds in the sky, then the sky is not completely blue. Now I say, you know what? I could make an entirely new statement and start here. If it is raining, skip the part about the clouds in the sky because that was repeated. Just say, if it is raining, then the sky is not completely blue. Okay, and that would be our conclusion, would be this final statement. So then this statement is also true. Alright, so 2 laws of logic today, law of detachment, law of syllogism. Let's practice these. First, we're starting with law of detachment. This is where I have an if-then statement, and we're trying to draw a conclusion. I'm using law of detachment. I have an if-then statement. If 2 segments have the same length, then they are congruent. Now, of course, this part is my hypothesis. This is my conclusion. This is true, right? If 2 segments have the same length, yeah, they're congruent. Here's my next sentence. I know that BC equals XY. Hey, remember how when you have 2 letters, that's talking about a line segment, but the fact that they're equal, what are we really talking about? This statement right here means that these have the same length. That's what this statement here is saying. If BC equals XY, these have the same length. And the reason I'm jotting a note about that is because here's what's important. Remember the hypothesis here? It said 2 segments have the same length. And didn't I just satisfy that right here? By BC equals XY, by knowing that BC equals XY, I know 2 segments have the same length. The conclusion you're going to draw is, what do you know about those segments? Then they are congruent. That's my conclusion. But instead of saying they are congruent, what's congruent? BC and XY. And I know to say 2 line segments are congruent, I need the line segment over the top. I need a congruent sign between. So my true if-then statement was, if 2 segments have the same length, they are congruent. I knew that the hypothesis was true. I knew that 2 segments here had the same length. Therefore, I know they're congruent, and I write that out. So that's kind of a geometry example. Here's an example with words here. If Nathan is enrolled at Metro High, then he has an ID number. Okay, and we're assuming that this must be a true statement. If Nathan is enrolled at Metro High, then he has an ID number. Here's what you know. Nathan attends Metro High. Doesn't that satisfy this right here? Hey, if Nathan is enrolled in Metro High, well, they just said he attends or is enrolled at Metro High. Therefore, my conclusion is what the conclusion was of the if-then statement. Nathan, or he, has an ID number. Because that statement was true, and that's what followed from him enrolling there, I know that he has an ID number. The conclusion is also true of that statement. Law of detachment. We did some practice here. Let's do some practice also with law of syllogism. Remember, law of syllogism is also called chain rule. And how that works is you're going to have 2 if-then statements. You should have the conclusion of the first one repeated as a hypothesis of the second, and you're going to make one final if-then statement that connects the first and second by eliminating that common conclusion and hypothesis. So first example, if Joe takes geometry this year, then he will take Algebra 2 next year. If Joe takes Algebra 2 next year, then he will graduate. What I'm noticing, did you hear something that was repeated? Conclusion of the first one, hypothesis of the second one. If Joe takes geometry this year, then he will take Algebra 2 next year. That's the conclusion of the second one, right? Here was my hypothesis, here was my conclusion. I repeat this exact statement as hypothesis of the second sentence. He will take Algebra 2 next year. Here it is. If Joe takes Algebra 2 next year. Repeat it as the new hypothesis. Then it says he will graduate, last conclusion. So what I'm going to do here, the fact that this is repeated, I'm basically just going to totally eliminate this chain that is common to both of them. Start at the first hypothesis, end at the last conclusion. So I'm going to start with, if Joe takes geometry next year, that was the first hypothesis. Joe takes geometry this year. and seeing that he will take Algebra 2 next year, then repeats that he takes Algebra 2, he will graduate, I can ignore that common chain and go right to the end, then he will graduate. I'm sort of implying that that middle step is in there. I know that if these statements are true, then this first hypothesis will lead to the last conclusion, since we had that repeated statement in there. Law of syllogism. Alright, let's practice this again. If y cubed equals 8, then y equals 2. And that is true, right? Because 2 cubed is 8. Next statement, if y equals 2, then 3y plus 4 equals 10. Let's make sure that's true. If y is 2, 3 times 2 is 6, 6 plus 4 is 10. Okay, both true statements, both if-thens. Notice something was repeated again. We had then y equals 2 was the conclusion of the first statement and the hypothesis of the second. This was repeated. This is the chain that I can completely eliminate. I can get rid of this common chain between the two. Start at the beginning. If I know that y cubed equals 8, I'm writing this new statement. Okay, I don't need to write this. This is implied. If y cubed equals 8, yeah, I'm going to know that y is 2. And look, if y equals 2, this is what I can finally conclude. So I'm going to jump right to the end, and that conclusion of 3y plus 4 equals 10. Again, eliminating that common statement, the conclusion of the first, hypothesis second, that was the same, and use the law of syllogism to write a new if-then statement. And last one here. If the radius of a circle is 4 feet, then the diameter is 8 feet. That is true, right? Radius times 2 is diameter. If the radius of a circle is 4 feet, then the area is 16 pi feet. We learned last chapter, area is pi r squared. Radius is 4, 4 squared is 16, and so yes, that is true. Both true statements. Let's see if we can use law of syllogism. Now I want to note what is repeated here. What was the same in both statements? It looks like the common thing is the radius of a circle is 4 feet. The radius of a circle is 4 feet. But notice something here. This is the hypothesis of the first statement. This is again the hypothesis of the second. Now remember, to use law of syllogism, you have to have I'll go back here, the conclusion repeated as a new hypothesis. We can't use law of syllogism here because we don't have one conclusion repeated as a hypothesis. Alright, so make sure that it doesn't trick you there. You need repeat as conclusion, new hypothesis, conclusion, new hypothesis. Hypothesis both times. Okay? So law of syllogism, law of detachment. We're going to look at combining our inductive and deductive reasoning, the two types of reasoning that we've talked about in this chapter. Now remember that inductive reasoning was done by looking for patterns, and then we made a conjecture based on what we observed. Whereas deductive reasoning, we have to show, prove, reason, use facts, okay, to really show whether conjectures are true or false. First of all, you need to know the difference. Decide whether something is describing inductive or deductive reasoning, whether it's patterns or actual facts and reasoning. And we have to be able to do both. Use both types of reasoning here. So, an example. What conclusion can you make about the product of two odd numbers? Okay, so I have to create my own conjecture, and then I'm going to actually use deductive reasoning and show that that conjecture is true. What conclusion can you make about the product of two odd numbers? First of all, I need to know that product means two numbers are being multiplied. So the question is, what conclusion can I make about when you multiply two odd numbers together? All right. Well, first I'm going to use inductive reasoning. I'm going to observe a pattern. I'm going to try some things out, see what I observe. So product of two odd numbers. I think we did this one before. We looked at multiplying two odds. 3 times 5, we get 15. Pick two more odds. How about 5 times 9 is 45. How about 11 times 7? Again, multiplying two odds, and I get 77. How about two more odds? 3 times 15, you get 45. Alright, can we make our conjecture? It looks like we get odd numbers no matter what when we multiply two odds. So, my conjecture, I think that the product of two odd numbers is always odd. But since we're doing deductive reasoning today, we're using reasoning, we're using proof, we're using a very step-by-step formal method, we have to use deductive reasoning and show that it really is true. We talked about the difference between odd and even numbers, and today we're doing odd times an odd, and we're trying to show that we get an odd number. Now remember that an odd number can be written as 2 times anything. I'll do 2x plus 1. 2 times anything is always even. When you add 1, you create an odd number. So my first odd number I'll call 2x plus 1. And I'm multiplying, so I put that in parentheses because it's a quantity. I'm going to multiply by another odd number. I'll pick a new variable. How about 2y plus 1? Okay. Now if I'm going to do odd times odd, I need to actually distribute here 4 times. 2x times 2y would be 4xy. 2x times 1 is 2x. 1 times 2y is 2y. And finally 1 times 1 is 1. Now remember what I'm trying to show. I'm trying to show that an odd times an odd equals an odd. Alright, trying to show this statement. So I need to turn this into an odd number. Remember, an odd number is written 2 times something plus 1. Well, if you notice, I have the plus 1 here. If I can make all of this be 2 times something, I'm good to go. And it looks like I could factor out 2 from each of these terms. So that's exactly what I'm going to do. Remember that when you factor out something, you leave what's left in parentheses. If you factor out 2 from 4xy, you're left with 2xy. If you factor out 2 from 2x, you're left with just x. Factor out 2 from 2y, you're just left with plus y. And I'm leaving the plus 1 at the end. I can't factor 2 out from it. And anyway, I want it to look like an odd number, which would be 2 times something plus 1. Well, isn't all of this just something? So over here, I'm going to write that 2xy plus x plus y is just a number, whatever it is. And we're going to call this something else about n, because it's a number, right? 2xy plus x plus y, all of this is just going to be a number. We're going to call this n, so 2 times all of that stuff we're just going to call n plus 1 at the end. And now you notice that this is an odd number. So I've showed that if you do odd times odd, you get an odd number at the end. So deductive reasoning was the step-by-step, very formal method, whereas we started out with inductive reasoning, just looking for a pattern, trying things out, and trying to figure it out. So laws of logic today, law of detachment, law of syllogism, and talking about using inductive and deductive reasoning to show a conjecture is true.